Hello, I'm Roman, and welcome back to a series of videos Neural Networks from scratch in Golang, where we using this book but implementing everything with Golang. And in the previous video, I finished with the binary logistics regression model, but it doesn't work. So what I'm going to do, I'm going to debug it. I checked the code during the last video and I found a couple of mistakes, but still the results are not good. So what I'm going to do, I'm going to compare two implementations. I took the one from the book and I'm going to compare the implementation that I have. In order to do this, I need to eliminate once again the randomization factor, and I'm going to do this by dumping create data and weights for the first layer and for the second layer. And then what we're going to do, we're going to mock it once again like we did last time. So we'll have the mock sample data and for two weights. The only difference now is I will have different sizes of the data. PyLSP timeout. Yeah, very hard. Because right now, for example, here I will have 200 sample data. Here I will have 64 neurons, so I will have 64 weights, right? And here I will have 1, right? Well, yeah. Well, number of neurons and number of the inputs. So what we're going to do, I'm going to dump again. And this is the second time as I'm doing this. So I'm not going to implement, something like real dump, something that will dump this data and then I can load it in both world, in the Golang and in the Python. Right now, I will do it same. I will just print all of the data and just hard code it into the code. But if that will happen third time, then I will definitely need to create some dataset generator that dumps it into some sort of the file that can be loaded then for the weights, for the datasets, and same for the Python. So I will have less time. Well, I will spend less time doing this, but let's go. And I actually want to do it in a different way. So if we take a look right now at how the mock data looks like, it basically, the declaration of the variable, its values equals to float 64 and some variables and some numbers inside. And what I can do, I can generate this string. Actually, I can generate two strings because if we take a look at how it looks like here, that will be like this. I can even add the reshape with the Go. I think it's a little bit different because I need to, but yeah, actually I can do. So let's do what I will need. I will need two variables, one for the Go string. Let's do it Go string, and we'll have Python string, right? How the Go string will start? It will start from this, from what? It will be values equals to float 64 and this opened one. For the Python, that will be, let's take a look. Yes, it will be return and p.array. this one, and that's it. Okay. What we're going to do next, then we're going to iterate over all of the values here. And I think I have it actually deleted it recently, but I did not commit it, so it should be easy to return the code to concatenate. No, not here. Foundation. Oh yeah, this one. FMT as printf, %f, and the value. Okay. So what we're going to do then, for the go string, it's equal, I think I can use this one, and it's fmt as printf, %f, and v, right? Then plus comma and space. And I think same for the Python string, right? Right. What we do in the end, for the go string, we append, what will append? We'll append closing, and then we can generate this part too, actually. What we can do, we can take the R and C from value dims. Why? You will see. So for the go string, we add closing one, then we go on for the next line. And then what we do result equals to mat new dance, mat new dance opened. Then I have R. I think, can I string conf string? No, actually I can as print. Oh, I think %d and R plus comma space plus no. Wait. As print. Actually don't need this. Print and C. And I think that should be closed. Oh no. Nil and then closed. Right? With the Python string, that we need to close this, then we write in reshape, opening, and then again sprint fr plus sprint c, and that. Oh, right. And I need to print them. And the Python string. Right? So make run. Okay. And by the size, I should understand what I'm mocking. So the first one is mock sample data. And that should be, I think, this one. Right? Makes sense? Makes sense. The second one is this. No. The second one is the dense first layer, which should be 2 by 64. This one. right? And then this one works. Okay, then what I'm going to do, so taking the first one, which is the two, this one, and we're replacing this is the first one. Um, Plot. Why do I undefined math new new dance? Okay, yeah, I totally made it incorrect, but okay. I mean, um, that's fine. I can fix it. The second one is, where is it? This one, right? Okay. This. Hmm. It's missing. Okay. Hope it's like this. Invalid. Compose. Yes, that's correct. Defined new dance and value. And the third one. And this is the last one. What new dance value? Good. Where I have the errors? So what I'm going to do next, what I need to do, I need to change three things. First, I'm going to overwrite. First, I need to remove this. Right. First, I'm going to overwrite mock spiral data. Why cannot use? Well, yes, you can. Okay, once again, where is it? Okay, we have the mock spiral data. Then after initialization, we override its weights to the data sets, mock dense 1. And we're doing the same for the second one, right? Mock dense 2. What it means. And then we need to do the same here. So instead here we using the data, right, from, I think, data sets, import mock sample data. Yes. Mock sample data. Come on, go. Then dense 1 weights equals to mock dense weight 1. Dense 2 weights equals to mock. So we have our results, right? Then we going to use range 2. What you don't like? This value of x is never yours. Okay, so the first thing we actually need to do is we need to be sure that I have the same data. How I'm going to do this? I'm going to, well, I can debug it, or I can just print it. It's hard to debug with this split. I mean, because the WI takes a lot of the space, and I mean, it's not that comfortable. So we have X, then we have, no, okay. Then we have dense one weights, right? And we have the second one, not here, this. Okay. We doing this the same. We're printing what X, printing then weights. And we have the second one. Okay. Fingers crossed. Clear. Clear. And Python main py. Alternative is no. Okay. Can I do this? Yes. Rep shape. Yeah. Okay. Weights percent. Rep shape. Shape. Reshape. Yes. 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 Okay, we have 1, 2, and 3. Right? Let's take a look. This is too much information. Wait. Okay. Let's just do it like this. That should be printed once. Do I have prints somewhere? Oh, right. Okay. That's good. 1, 2, 3. Yes. Okay. Then I'm doing the same here. Make run. And boom. 0, 0. Okay, this is the same. The second line is the same. Let's take a look at the last. And the last line. 0.965265. Okay. And checking the... Okay, they're the same. 2893. Okay, the last one, 242. Okay. They are the same. What it means? It means that I can now do one epoch here, and I can do one epoch. I don't think I need this anymore, and I don't think I need this anymore. So no. Change in sites. Yes, I don't want to. we have this one, have this one. My assumption that I have a problem with not that should be the same. I don't expect any problems here. What I think is the calculation of, well, actually, that should be okay. I think the main problem is activation of the loss function, right? But let's take a look. So the first thing we testing is printing the results of activation to output. And here the same activation to. Okay, so the last one is the same. The first one is 0.5. There is a 0.5 somewhere. Okay, this is just the precision higher, but I mean, it's the same. Okay, I implemented sigmoid correctly. Um, okay, let's actually take a look at accuracy if we calculate it properly. Where is it? Print accuracy 0.89. This is interesting. So the accuracy is different. But why? Given the arithmetic mean along the specific return, the average of the array elements. The average is taken over the flattened array by default, otherwise over the specified axis. Float 64, intermediate, and return values are used for the. Okay. Calculate accuracy from output of activation 2 and targets. Oh, okay, so wait, okay. So this is actually fully incorrect. First, I need to calculate, I need to understand the predictions, which is okay. Preds equals to maths, then scope of predictions. Okay, preds apply if b is bigger than 0.5, return 1, otherwise return 0. And I'm passing the predictions here, right? Print len pred predictions. And then we are calculating. Okay, what it means, predictions equals to y, what it will return. I guess it will return. Okay, so that's actually, I will do it differently. That will be preds make int 8 plan predictions this, then we for I 0 I less than plan predictions, right? Expected to pull in a range of the expression, but found simple statement. So if wait, for I value in predictions, that should be better, right? It's range. Okay, if b is bigger than 0.5, then threads it equals 1, else threads. Okay. Then I'm calculating the average across successful predictions. So I actually using count equal to 0, right? Then what I'm doing range again for I in the range of pred. I assume that it's the same as the target classes. And what we do, if pred equals to target classes I, then count plus 1. And what we return count plus 64 count, wait, count divided by len of pred. Yes, plot 64. Okay. 0.49. Okay. So we actually change. Okay, so the calculation of the accuracy was incorrect too. I mean, I thought that will be much simpler, but turns out I made so many mistakes. I mean, but it happens. It always happens. Assume predictions len is equal to target class. Okay, so run binary. Okay, so we have the same accuracy right now, right? Okay, and then we have epoch 0, accuracy 10.59, loss. And this is data loss, regularization loss. They actually have it 0 for some reason. Learning rate, the same. Validation accuracy 0. Okay. Wait. So there are actually two questions. Why the regularization loss is 0, right? Because I mean, I understand why the regularization loss is 0 for the second one, but why not for the first one? And I have some value for the regularization loss, which could be the case too. Weight regulator, bias regulator. Interesting. Okay. Okay, with the accuracy, it's clear, right? Uh, we have the small decay. We have, okay, check layer regulator L2. Yes, that's a small value. Accuracy is okay. So the next thing is data loss. Okay, let's go. Let's go. This is the interesting one. So let's take a look. This is the one. That's not, this is the activation sigmoids. This one. So we have the sample losses, right? Just take a look at the sample losses. I'm pretty sure that's where the problem is. For methods and sample losses. Oh, right. This and hmm, 2. Why I have it second time? Calculates. For the right. We have it second time for validation, and I should have the same. I need to clean up. Wait. I don't get it. It still prints me this. Okay. Maybe just a problem with history. Okay, so this is kind of the first problem, right? Minus, they all positive here, but mine are negative. But the values 146 693 and what is happening? Wait, binary Kursk. Okay. Oh, so it's a big minus. Oh. So we have target value multiplied by the logarithm plus, again, target value multiplied by the logarithm. And then we calculate mean value. So that's the issue? Really? Really? Well, I still have the question about the regularization loss, because here it seems it's non-zero. Okay, binary, no, run binary model. Okay, imagine you telling me that it will be okay, right? Oops. Whoa. Read. Okay. I have more issues. Wait, that's not the case. And so we're still testing it. Okay, assuming that this is the correct now, right? We have the sample losses. Okay, let's, what will be the value? Print, empty print value. Print data loss. Okay. Loss, 0 point data loss. Data loss 69 loss. We have the regularization loss for some reasons. We have, oh wait, no, learning rate is the same, accuracy is the same, loss we have 0.3, have the regularization loss, which is 0, like purely 0, and we have the data loss. Okay, run binary model. And we're not finished with actually the backward method. There is a backward method actually. That's I had the problem with this one, right? By the way, that probably will be the same binary. This one. So again, there is a minus, global minus. Okay. Okay, let's take a look with regularization loss. No, it's a backward path. Where's the calculation of the regularity loss? Reg loss. Okay. Def regression loss calculation. Okay. Still 0. Oh, okay, so it's okay, so it's small, it's just the print statement. Okay. Okay. Run binary. Okay. Okay. That means that the the forward path is correct. Is correct. What it means then? Then it means that, well, the optimizer is the same, so we need to track changes in the backward path. And one thing that was changed a lot is, well, actually the loss function, which is loss function d inputs, right? And we're doing the same here. 50 print activation 2 d inputs. FMT print ln ln mat. Wait. Where is the data? Oh, loss function. Interesting that it's not crashing. Minus what we have here. Um, they are very different. They are very different. Okay, loss function backwards. Loss function binary percent will loss backwards. Mhm. Девять восемь 9998. Okay. And 0.5 and begin. Okay. So far, so good. All right. Then wait. So far, so good. This. It feels like there is some. Okay. Loss. The inputs equals to math new dense. Sample count, output count, nil, right? Okay, let's try again. If 4 equals to 0, I less than sample count plus plus for j equal to 0, j less than output count, j plus plus, and plus the inputs. Okay, we're calculating the value, right? And the value is minus y true divided by the clipped d values. So it's target. Target I. Okay, float 64. Targets I. Target I divided by d values at I and j, right? Minus 1 minus targets I, right? And it's float 64. And then it divided by minus d values clipped I and j. Okay, and then divided by outputs count, and then divided by sample count. right? And then loss the inputs set ij value, right? How? How? Why? What I did wrong? I feel like I'm stupid, which, well, probably I should feel like this. Okay. And I think this is the, not here, not here, this one. Run binary. Do I have new backwards method here too? Well, yes, actually, we have this one too. Duration 2. And we need to check it. Instead of the loss function, that will be activation 2. Okay. I'm checking the last value and the first one. Okay. So then if I print then swan the inputs, right? I should have the same values. Okay. I am ready to party. Okay. Let me try to actually train it once again. I think. Okay. Accuracy 84%. Validation data loss 0.44, accuracy 79.5. Let's try here. Interesting that the difference in accuracy is, well, there is a difference in the accuracy, but most likely it's the, oh, I didn't mock the testing data, right? Yes, so it's actually not valid for me to check the how the validation. But if I take a look at the epochs, that should be more or less the same. So for example, I have the accuracy 84%. There is the 8065. Okay. Loss is less here. Data loss is 0.32. Well, maybe I still have the differences in the optimizer. Okay. So there is a decay and decay epsilon is beta 1, 39, saturation is 0. I mean, there should... Well, maybe there is a difference in the calculation. I'm not really sure. But we're using the same Atom optimizer with the same regularization, same number of nodes. I mean, okay, the difference is not that big. I've checked all of the calculations and there might be changes, differences in the calculation, and they just stack on top of each other. Maybe I'm wrong, but I mean, so far, this looks like a valid thing. I mean, the model is training, right? And if I try to use... And if I will try to use it once again on purely random data, I mean, the loss is going down. Actually, I think we need to do same here. Yes. I mean, there is a good accuracy. For example, the accuracy here is 865, but on the testing data, well, here's 86%, here's 81. So that tells us that it goes towards memorization. So maybe we have too much of the layers. Maybe there is something else. We have a pretty low learning rate. We have low data loss. Regularization loss exists here too. But I would say it's actually so far so good. At least I would consider that I found all of the problems, which I actually made a lot of them. By the way, what was the last? What was the last issue? I mean, I just want to recap how many things I did incorrectly. First, there was... No, this was correct. The binary cross entropy loss was implemented purely incorrect. Both places had issues. Then I had an issue with accuracy calculation, which is, I mean, surprisingly stupid, but I mean, that happens. And yeah, I think it took me probably much longer to find all of these issues if I didn't have these example codes, which is I'm still trying not to use them. So far it was the second time when I actually had to dive into the Python code and compare the results. But it happens. It happens. And there is nothing wrong with it. Yeah, calculate accuracy. The model performed quite well. You should have some intuition about tweaking the output layer to better fit the problem. Tweaking the output layer you are attempting to solve while keeping your hidden layers mostly the same. In the next chapter, we're going to work on regression, where our intended output is not a classification at all, but rather to predict a scalar value like the price of the house. So that we will do in the next chapter. And I see already I will need another data set to do this. Probably I will implement it meanwhile in between the videos, because, well, we'll see. Maybe we'll start this from the maybe we'll start this from the next video. But so far, thank you for watching, and I see you tomorrow. Bye bye.